because there's another guy coming in at 11, I think, 11:15. So I wanted to get started, and my name is Gregori, and today I'm going to talk about open source project I'm working on called the RobotVisionToolkit. And the idea behind this is it's a toolkit for people to get started in robotics, people to, well, let's get started on the presentation. First of all, I wanted to bring up, I noticed yesterday when I was at the presentations, lots of people on their laptops. Everything I'm going to talk about here, you can download at this website, www.emgrobotics.com. It's actually the last thing right here. So all the software and everything is right here that I'm going to be talking about today. There's a reference manual in there, and then this presentation, I'll put it up there as soon as I get a chance today. If I can get Wi-Fi in here, I'll pop it up there today. Also up here, if anyone's interested, there's some computer vision. I travel the country doing computer vision training, and I video record the trainings. The PowerPoints and the trainings are up in the computer vision training tab. And then I also do classes on embedded Linux. So if you're interested in embedded Linux, Linux primarily on ARM processors, you can go to the Linux tab, and there's various videos and PowerPoint trainings up there. So the goals for the RobotVisionToolkit. Number one, the primary goal was to provide a simple, all-in-one tool for people to build smarter robots. I go to these there's a robot club called Chibots. A lot of people involved in robotics who are not traditional software engineers. A lot of mechanical guys, a lot of electrical guys with some software knowledge, but not much. And when I saw that, what I wanted to do was provide a tool for them to be able to take advantage of some advanced software concepts without having to know all the ins and outs of C++ and APIs and so on, Windows API calls or Linux API calls. The second comment there, the toolkit's so simple that even a manager can use it. That's actually something my manager wrote. He's not a software guy at all, pure hardware, and he was able to get up and running building robots. As a matter of fact, he did this one that can walk and so on. He was able to do that within a couple of days. The other thing I wanted to do was build something that would grow with the user. A lot of people start out in robotics using something called a basic stamp, a parallax basic stamp. Great way to get started in robotics, but the problem is that you're really limited in what you can do. So what I wanted to do is provide something sort of the next step. You get done with the basic stamp, you work up to the next robot, and then you can grow with it, and you can go all the way up to adding vision. Here, let's go to the next slide here. The toolkit itself is actually expandable, so you can actually add stuff to it yourself. I mean, I'm sure everyone in this room would be more in that category. So you got the ability to add keywords and be able to expand to the language. So like I said, why did I do it? Again, the people who are into robotics, a strong desire to play with current technology, a strong desire to move on towards the smaller robotics that they started with. And in terms of something that this would be similar to, from what I've read, it'd be similar to the Microsoft Robotics Studio, the same kind of concept, I guess. Also, RoboRealm, if you're familiar with that. If you're familiar with OpenCV, the whole point of something like this is to take OpenCV and make it usable by someone who's not an advanced C++ programmer. Now, I don't use OpenCV. I actually have my own. All these algorithms are my own that I've written because they've got to run on various embedded systems. So an OpenCV doesn't port as that well. The other thing I wanted to do was provide a path for kids. So right now there's not a whole lot of things out there for kids. There's a lot of interest in using robotics to get kids into technology. If this is something, yesterday the talk was about starting your own companies, doing your own startup. Let me tell you, getting kids involved in technology is something that we really need. And I think he even brought it up yesterday. We just don't have anything like that, and robotics is a very good thing to do that with. And then I always get the question, why did you create yet another programming language? The primary reason was I needed something that would, again, for people could use it who are just familiar with BASIC. Now, this is sort of the wrong crowd than who I normally speak to, but normally I ask, how many people here have programmed a Commodore 64? Everyone in the room's hands go up because we're all 30 plus years old. You guys probably never even heard of them or saw them in a museum. So in this case, Commodore 64 and Apple II Plus, guys my age, we grew up on those. Everyone knows how to program those. Anyone who's my age at one time programmed in BASIC. So the goal here was to start out with people like that who programmed in BASIC, give them the same look and feel of that Commodore 64 or the Apple II Plus, but then allow them to transition to a more advanced language like C. Okay? The toolkit was, I started it out in 2003. It started out as a computer vision library. Like I said, I needed to write a library that was easily portable across all the embedded systems. This particular library will even run in a small 32-bit systems with something in 64K of RAM and so on and so forth. So it's very portable. The Linux or the Windows versions based on AVI-Cap, Linux versions based on GStreamer. Excuse me, and the WinCE version is based on DirectShow. In 2007, I got involved in a project called RobotMagellan. It's a competition that we had, and I'll have some slides on that. And this is when I discovered that there's a lot of people out there who are very interested in robot vision and advanced robotics who do not have the software training. Okay, and this is when I decided, hey, these people could use this library. And sure enough, some of the people in the competition actually used the library. The problem we had is at that time, there was no way to communicate with the library. You still had to know C in order to use the library. So in 2008, after various attempts to make this vision library available to people, again, with not a lot of software knowledge, I finally, after a lot of research, decided to write this language called Robot C. And that's one of the things we're going to talk about today. And again, the goals for Robot C was easy expandability. For advanced users, you can add your own keywords. You can completely change the language. It will be open source. The source isn't public yet, but it will be available by the end of the year. So you can change it and do whatever you want. There's a graphic IDE. There's a debugger. Everything's there for it. And then just in the last year, it's just taken off. So I've added all these advanced features. There's voice recognition using SAPI. There's this robot that the company I work for decided to build to sort of, we'll talk more about what the robot's for later, but the idea behind the robot is for a classroom environment for these classes that we travel around doing, teaching sensors. Joystick interface, web HTML, TCP/IP interface, all this stuff that you guys are probably used to. You guys can code no problem, but someone who doesn't have the experience would have a real hard time coming up with TCP/IP interface or a web interface. They can do this in Robot C and basically in a basic type language, including graphics. So I brought up RobotMagellan, and I wanted to bring this up here because I think this is I don't know if you guys haven't heard of this. This is something very exciting to get involved with. RobotMagellan's a mini DARPA challenge. So I'm sure you guys have heard of the 2005 DARPA challenge. The idea behind RobotMagellan is the same concept, except for a smaller scale. You go out in a room, I think it was 3,000 square feet, or 3,000 by 3,000 or 6,000 by 6,000. You go out in a huge field, let's put it that way. And the idea behind the field is they put some cones out there. You can't see all the cones from the starting point, and using GPS and computer vision, you're supposed to set your robot out, and it's supposed to autonomously find cones. So this one down here was my entry, and this robot was done using the RobotVisionToolkit. And basically, the idea behind it is almost all my robots are laptop driven. I use these little netbooks because you can get them so cheap. So in this case, it was driven by an Asus EPC. There's the top of the robot without the computer on it. You can see there's a little 8-bit micro on there to convert to USB. And this stuff's all available. USB to commands for the truck. And then the robot, or the EPC, handled GPS and, I got a block diagram down here, and webcam running the RobotVisionToolkit, controlling the robot. And if you're interested, because I know one of the big problems, again, there's no one's got all the skills required for robotics. No one's an expert mechanical engineer and an electrical engineer and so on. So if you guys are software guys and you want to get a platform up and running right away, actually up on YouTube, I got instructions and videos on how to build this from a toy you can get at Toys R Us, and the toy is actually still available. And it's really easy to build, and it gives you a really nice, solid, that truck is 4 feet long, so it's about that big. So it gives you a really nice, solid base for a robot. So this is what I look like after coding for 18 hours. I actually put this slide together without realizing how bad I looked in the picture. But yeah, so this is the RobotVisionToolkit. This is actually for our classroom environment, so some extra things in there that aren't part of the standard kit. This is for controlling and manipulating the robot to get some calibration numbers. basically what you have encompassed in the kit is it starts out with robot C in the center. So the robot C language is the center that ties all these other software bundles together or packages together, whatever you want to call them. And the way it works is with robot C, you can get up and running again, just like you're on a Commodore 64, just like you're on an Apple II. You can start running, you can do print statements, you can get all that stuff that everyone starts. You can do your hello world. You can do all that right at a terminal. You can do it in a terminal, you can do it in a GUI, you can do it however you want. What you can do, though, then, is you can instantiate, by doing a simple load call, you can instantiate one of these, and in Windows they're implemented as DLLs. You can implement one of these packages. And what happens is when you add the package, it automatically adds not only the hardware side support, but it also automatically adds the keyword support. So I'm going to talk about that a little bit more later, but the idea behind it is, from a user point of view, I don't need to know all the stuff that's going on behind, let's say, SAPI, which is what I use for text-to-speech. I don't need to know all the stuff that's going on behind there. Okay? All I know is I load up the SAPI interface, and I get 2 or 3 extra keywords, and using those keywords I can talk, I can do speech recognition, and so on and so forth. And again, the motto here, as I was coding this language or creating this language, as simple as basic with the power of C. I wanted something that allowed people to easily transition from here up to here. Now, that's going to give the language a relatively short amount of time that it's going to be in existence, but that's fine. The goal here is to get people into robotics. Now, the point of this language isn't to necessarily teach someone programming. The point is to get someone up and running with a robot and get them interested in the concept of going beyond here. Okay? So what you can do with this language is you can build some pretty advanced robots, and I'll show you what you can do. I've got some video here. I didn't actually bring the robots because I wasn't sure what I'd have. I just got one, and I've got a little demo over here running. But the idea is you can start out here. This is where my boss is at. He uses all global variables. He does everything with real simple loops and stuff like that. That's why he's in management. And then you get to the more advanced stuff up here, where you can start using things like switch case. You can use C-type arrays. You can do much more advanced stuff on this side. This is all in one language, so you can do whatever you want. I've got enums, I got tables, all this advanced stuff on this side. And you can use them, obviously, it's all keywords within a language, so you can use them interchangeably if you'd like. So I mentioned before that the language itself is expandable. So what I got over here is just, these are some things that are built into the sort of the key language. Again, everything you'd expect if you've ever worked on an Apple or a Commodore, file I/O, serial port support. It does have math and floating point, which we didn't have back then. Time, multitasking. Oh yeah, and it is multitasking. That was the other thing. So again, when you get into advanced robotics, you want to do single thread, just not going to cut it. So the language itself is multitasking. On top of that, of course, the extensions, when you add them in, will kick off threads too, so they run in the background, but you don't really need to know about that. They're handling themselves. But you can also kick off multiple instantiations of the language in the interpreter, and then there's a mutex that lets you talk between them. There's interrupt support. I use subroutines instead of function calls, again, for simplicity. And then you've got your basic decisions. So let's take a look at the computer vision language extension. So when I load the DLL, when I load the computer vision language extension, and I'll show you what that looks like, what that does is that adds these keywords to the language. Okay? So there's what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it adds 10 keywords to the language. That's what the user sees. Okay? He doesn't have to do anything. He loaded the language extension, the DLL, and now all of a sudden these 10 keywords pop up. And of course, we know in the background, all the hardware drivers and everything that had to be on this side, all the Windows stuff in this case, popped up and it's taking care of itself on this side automatically. So you go ahead and you load that up, and it's the same with the robot, by the way. So the core language doesn't have any concept of hardware other than file I/O and serial I/O. So in this case, this is a USB robot. So on this side, when it loaded up, we call it Kevin Jr. That's the name of the robot because that's the name of my boss. So when it loads up the Kevin Jr., when you load up the Kevin Jr. language extension, boom, all these keywords pop up. that automatically give you access to the hardware. So you can read the sensors, you can read the touch sensors, the accelerometer in here. You can go ahead and you can do I2C read and SPI write, I2C read and write, SPI write and read. And what that lets you do is in the classroom environment, we use this as like a teaching aid. Okay, that's why it's small and that's why this is what it is. We might have, in the classes that I do, we might have 20 of these in a class. Each person sits down and we spend the day learning about sensors, using the Robot C language and using this robot. So, and the beautiful thing is we've done one test class, well, we've done 2 test classes already, but only 1 full hands-on. And the language worked. People were able to get up and running immediately. It was only a 3-hour class, and people were writing code at the end and actually using the robot. So there's 2 ways to do computer vision in this particular language extension. Again, for simplicity, there's the pre-built filters. And I think that's what I'm demoing here. So the pre-built filters are, for instance, color blob tracking, off transform circle tracking, motion detection and tracking, and HAR feature-based object face detection. This is sort of based on Viola, however you pronounce it. But it's the end process is the same. The learning is actually different. So those, a customer or a user, he can just load up that algorithm. Let's see if I got examples. Yeah. So this is actually code to use. This is actually code that's going to be running in the demo. I'll show you the demo. So this is the Robot C code. First of all, what you'll notice is not a whole lot of code. There's a lot of prints in there. And what you'll see is that first at the top, I load the DLL. That adds the keywords for computer vision and handles everything else. It actually kicks off a whole bunch of tasks, but again, the user doesn't need to know anything about that. Then I'm going to load up the filter. And in this case, I'm loading a pre-built filter. So I'm going to load up the color tracking filter. And then using the vision write and vision read keywords, I can send the filter parameters. And I can read data back from the filter. So the filter is I'm going to go ahead and configure it. And I don't have the set threshold code. It wouldn't fit on the slide. But it's going to go ahead and it's going to set a threshold using an iterative approach. And then on the tracking side, I included the subroutine for tracking. It's going to go ahead and it's just going to read a variable, which is going to be a position variable. It's going to split it up because it's x, y as a single integer. And then it's going to go ahead and track. I think in this case it tracks or just prints the data out to the screen. Again, I'll show you the demo. The other way of doing computer vision is again, the idea of being able to go from simple to more complex is you can create your own vision algorithms. Okay? So how do you create your own vision algorithms in an interpreted language? Robot C is an interpreted language. Well, anyone who does computer vision knows there's no way that's going to happen. So I use the same concept as GStreamer, if you're familiar with that, or DirectShow. So in GStreamer and DirectShow, you build, and I'm sorry if I start using the terms interchangeably, but you build graphs out of things called elements. And I think I use the terms interchangeably. But the idea behind it is if you think of Legos and you think of bricks, you're going to stack these bricks on top of each other, and the whole thing overall, one side's an input and one side's an output. And those things in the middle are called elements. And each element does something. Okay? And in GStreamer, it's a pipe, and you take elements and put it into a pipe. But so what I do is here's your elements. Here's the blocks that you can play with. Each one of these blocks you can stack on top of each other, and each one of these blocks has parameters that you can set and data that they output. And then you use, again, Robot C, and it's actually just 2 keywords. You're going to go ahead and you're going to build your graph. So you're going to add these elements with various parameters, and at the end you're going to kick it off and run. Okay, now each element is going to have different data available from it, which you can then read using the vision read command. And that lets you create your own graphs. And because this is what's actually happening here is each one of these elements is being put into a C array, and it's flying through this. There's a thread flying through that C array. So this is actually running in real time. When you hit vision run, it kicks off that thread, and this is running in real time. And then there's a vision stop command, so you can stop it, you can reload, and so on. And here's just some examples of things that I've done. These are various robots that I have. This is a Chibot competition where we go out and pick up. And all these videos are on YouTube, by the way. Somewhere in here I've got the window. But This one goes around and picking up various color balls and putting them into a bowl. And I got video of that. Actually, my youngest son's in that video. This is the Robo Magellan that you've seen. This is a robot arm. I'll show you a video of this in a minute. And this is the robot that's up here. And there's just some some vision filters up there running. So let's talk about an application of this. So this is going to be, I'm going to show this video. This is going to be a robot arm. And what this robot arm is doing is using a color track algorithm to track balls in a, this is designed to be a desktop display. And the thing about this was I show this at iHobby. I don't know, any of you guys have heard of iHobby Expo? It's actually coming up next weekend. Oh, if you guys haven't heard of iHobby, it's a long drive for you. But if you haven't heard of iHobby Expo, it's in Rosemont. And for hobby robotics and basically RC planes, RC helicopters, anything like that, it's great. It's next weekend. And I think it's like $5 to get in. And it's at the Rosemont Convention Center. And we have a whole booth. There's 2 or 3 of us. There's our club. There's a couple of companies there. Whole line of hobby robotics. Everyone in the hobby robotics field that's in America will be there. And it's a great show. And this is a demo that I bring. And some of the issues that I had, if you're into computer vision, was no control of lighting. You know, this is a tabletop thing, so you got people over it, so there's shadows. So absolutely, yeah. So you guys are shaking your head. You guys do computer vision. So there's zero control of lighting. No control of shadows. So you'll actually see, if you look closely on the video, I got a ceiling fan running up there just to simulate the worst lighting condition I could think of. And you can actually see me creating shadows over it to make sure it finds the ball. So this is going to be an example of that. And this is, again, RobotVisionToolkit's running on a laptop that I got connected. There's a little USB servo controller here, and it's controlling this robot arm, which in this case happens to be a Lynx Motion robot arm. So let's go ahead and play that. I hope you guys don't mind videos. Normally I do these examples real time, but wasn't sure. Let's see. In UI. Okay, let's go ahead. There's music too. So again, it's up on YouTube if you want to see it. I've got 20 or 30, actually 34 videos of robots up there. So just doing all kinds of stuff. And if there's any information you want about any of them, you can go to my website, and it's all up there. Next feature in Robot C that I wanted to talk about, the Robot Vision Toolkit. And I'm not going to talk about all of them because I'll bore you guys to death. But you can go up there, and there's actually a reference manual. I brought a copy of it, but it's up there. It covers some of the stuff. But TCP/IP support. So again, how do you do TCP/IP if you've ever coded for sockets? How do you do that in a simple way in BASIC? Well, the way I decided to go with that is by basically making it completely run in the background. So the way it works is you establish a connection by calling a pipe con. This is, again, a keyword that's added when you load this up. He's already opened himself up. You're going to call, the client's going to call the server with the IP address. It's going to specify the variables, and these are going to be global variables, that he wants to share. And this guy is going to specify using the same variable names on this side, the variables that he wants to receive. And in the background, there's a thread that automatically shares the variables, and they're flying between them. So from a user point of view, all I got to know is it's a global variable. And in this case, when you say global, if you specify it here, it's global to the whole world because everyone, it's going over the internet. So you got basically a global variable over here. It shows up over here, and then there's a synchronization. Now, if you're really thinking about it, you're like, wait a minute, though. You could run into some real problems there. What if they both set to global variable? You can run into some synchronization issues. And that's where the advanced user concepts come in. So there are synchronization commands that you can also add. The idea behind that is that's something that most likely you're not going to need until you get a little bit further advanced and start doing some more advanced concepts. But that kind of synchronization is also available. And like I said, it does have an IDE and a debugger. Again, for simplicity, you can do it from the console if you want. You can actually, one of the requirements for it, a particular user was looking for was he's running it on a little VIA computer, a little VIA headless system, and he wanted it to power up and run right away. So you can run this from a batch file. You can just put it in autoexec.batch, kick it off, and it runs right out of the box because a lot of robots are going to be headless systems. So you can run it from a batch file. You can run it from a GUI. You can run it. The interpreter's a DLL. The DLL I can make available. You can have your own application and include the language in your own C++ or C application, because the interpreter itself has a DLL interface. And the interpreter, if you want to do something like that, the interpreter also has something called an application interface. So now, let's say you wrote your own whatever, okay, and you wanted to include Robot C and whatever. There's actually commands built in to allow the user to communicate with your stuff via a stream interface, and you can go back and forth now. So now you have a stream between your application and the interpreter. So anyway, in terms of, this is everything you'd expect in an IDE, and the reason I really wanted to bring it up with this particular crowd is this is based on the Scintilla open source library, and yeah, you've heard of it. This is great. I tell you, don't even try to use it. I don't know if you guys, I'm assuming you guys are all computer science here. Do you guys do Windows programming or Linux programming? Is it yes, both? Okay, so don't even try to use, what is it, the RTF control or whatever in Windows. Completely useless. So yeah, whatever it is. Go with Scintilla. Scintilla's great. It's got Apple support. It's got Linux support. It's got Windows support, obviously. And it works fantastic. There's lots of great example code out there to get you up and right away. So yeah, I went with Scintilla with this. I got this up and running in one day using Scintilla after spending a month trying to get the, I think it was the RTF or whatever control working. So what you can do then is there's a debug and a run. If you click on run, it runs your code up and running. If you click on debug, it's going to open up the debug window. And from here, you can go ahead and you can step through code. You can type in a variable name on the side, add a variable, and you can actually monitor a variable real time, because remember, this is interpreted. So you can actually monitor variables real time. And obviously, if you're into robotics, or you've worked with robotics, you know that the worst thing you can do is halt your program when the robot's running. That's never a good thing. That's always bad. So I've also added a data grapher. So what you can do here, and this is actually unique and different. I haven't actually seen this anywhere else, but maybe I'm wrong. Okay, so before, you can type in your variable names and you can monitor variables in real time. With this, you type in your variable names here, and you can graph your variables in real time. So I use this a lot for demos. With the robot, you can actually see the closed loop control system. You can see all the variables running real time while it's balancing and stuff like that. And this is just a slide from one of the labs that we do. Now, I've been talking about this little robot up here, bringing them up every once in a while. So again, I developed this toolkit. My boss said, hey, that's a great idea. My boss is, one of his responsibilities is sensors, okay? So what we did was, the problem they were having, well, let me explain their problem first. The problem they were having is they would do these all-day sensor classes. I'm part of a group that does classes and does training. And I'm the software engineer in the group. And so they were doing these sensors, these sensor guys were doing these classes, and the idea behind the classes is you'd work with sensor algorithms. And the problem was that you had to know C in order to play with the algorithms. Well, people coming into the class, they don't know C. I mean, they just didn't know it. And we ended up spending most of the day just learning C and doing training for them on C. So my boss heard about what I was doing. We put the two together, and he started using Robot C and the Robot Vision Toolkit on this. And it's got a little USB board. Okay, and this is all available source. So there's a micro on here with a USB stack and everything running, and then there's an accelerometer sensor and a, let's see, right? Yeah, right. Can you see a cursor? Yeah. So there's an accelerometer right there, and there's a touch sensor. And in the class, we interact with the sensor, and we experiment with algorithms and so on, all using Robot C. If you are interested in USB, I just threw this slide in there just because it's a bunch of free information that you might be interested in. There's all these app notes up here. All these app notes cover USB very thoroughly. So if you're interested in embedded USB and something you want to play with, these app notes give you all the information you would need to play with embedded USB. And then we actually have a free stack if you want to download it, and you can get, contact me if you want to experiment with some free hardware. I'll get it to you, and you can write your own USB stuff. And this particular app note, this last one, actually talks about the software that's in the robot. It's a different looking robot, but it talks about the firmware that's in this robot. And the board, we made it generic. It controls up to 8 servos, has the accelerometer. It's just a nice little controller board. And this is the block diagram. Everything's running on one micro. The one micro does pretty much everything that you need. And that's just an idea of the schematic. It's actually a very simple system. Now, what's interesting is right now the interpreter is running in the PC. But I'm working on a port where the interpreter will actually run directly in the micro. So this is this case, this is an 8-bit, but there's a 32-bit equivalent. It's a small 32-bit micro, and the interpreter will actually run in the micro. Now, okay, that's pretty cool. You'll be able to program it. You program it. There's a serial flash. You'll use the IDE. You'll be able to send your code down. Debug your code, get it up and running, send it down, unplug, and now the robot's running completely autonomously. But what about vision? Well, we actually have a little SPI camera that will also plug into the robot, and you'll be able to do vision on the embedded system too. Now, the algorithms are going to be a little simpler. You're not going to be doing Viola Jones, at least not the full frame, but you'll be able to do vision right on the embedded system. Okay, and that's on a small scale. And again, that's for this whole robot's less than $100. Okay, I'm going to talk about a little bit better computer vision reference design here. It's slightly more expensive. So just in terms of accelerometers, I'm not sure if you guys are into robotics. This is a sensor that you're going to use. So I threw in some slides from our accelerometer group on how these things work. Basically, an accelerometer is a moving mass. These pictures are pretty cool because these are the actual what's on the die in the MEM. That's actually a zoom in on one of the little circles on there. And this is how accelerometers work. This is a 3-axis accelerometer. And what they do is that there's a change in capacitance, and you're actually measuring the change in capacitance. And from that, you can get the displacement of the mechanics of the mass, the displacement of the mass, and then you can get a measure of accelerometer. And I'll do a little demo here. So what I've got is that 3-axis accelerometer in the top of the head. And let's go ahead and do a demo using the robot. Oh, let me get this here. Okay. So what we're going to do is, well, we're going to demo the robot. Of course, it's not working when I go to demo it. Okay. There it goes. So what we're going to do, so as you can see the XYZ. And so the console window in the background is Robot C running. You see I did it from a batch file. Now what's cool is you'll see the Robot C graphics. What happened was, as we were doing the class, the sensor guys started coming to me and saying, hey, Eric, we want to do some graphics. We want to do some cool stuff. We want to basically imitate the iPhone. And, could you do that? So I started coding all this stuff for them, and I did it in WinCE, so I do it in a Win32 API. So I started coding all this stuff for them, some video games, some quick demos like this, and they just kept piling it on and adding it. And finally I said, look, you guys do it. What I'm going to do is I'm going to go ahead and add graphics capability to Robot C, and then you guys can do it in BASIC. So this code right here that's running right here is actually entirely written in Robot C. So the way that works is, again, you load up a graphics library, a graphics language extension, and I try to avoid the word library because library scares people who don't understand what it is. So you load up the graphics language extension, and it adds, I think it's 11 keywords last time I counted. It adds 11 keywords. With those 11 keywords, you can do bitmap graphics. So you can go ahead and you can specify that a bitmap be a button. You can put the button anywhere on the screen. You can specify that the button be animated and change. There's up to 16 different planes, so you can hide. A common thing is you'll have a button. You might have multiple buttons with different graphics, and you just move them between planes when you want to animate them when they're pushed. You can go ahead and you can have a background. So you can do all this without any knowledge of the Win32 API that's running in the background, or the the GTK that's running in the background for Linux, or in WinCE, because this is also ported to WinCE. So again, now you can do all this. The guys in the group with these 11 very simple commands can do pretty much any demo that they want to be able to do. And they can do it for the desktop or the WinCE, an embedded system. And then this is just the demo that I just showed you. And I think I've got, and this is the demo that I just showed you. Let's see, let's go back here, go here. So this thing right here, so this includes reading the accelerometer, doing some filtering, just a very minimal amount of filtering. Actually, it's just conversion. And then doing all the graphics. That's all the code in Robot C. So very, very simple to do. And I think, isn't his face also turning? Yeah, I got his LED's face turning too. So again, very easy to do. You can do a lot of cool stuff with very little amount of software knowledge. I know you're thinking, but what about our jobs? Believe me, don't worry about that. One of the cool things about software, if you're going into computer science, is people will always need you. I mean, it's a great, great thing. Anyway, so I brought up this. I was supposed to kick this off later, but there's multiple ways to kick off a Robot C program. You can double-click on a batch file. You can open it in the IDE. You can also just drag and paste. The .c files are the actual source code. You can drag and drop them over the IDE, and they start running. Okay, so one of the things I wanted to be able to do is port it to multiple applications or multiple systems. So what just happened there? It started saying something. It's talking. Sorry about that. So this is this is a Freescale product now. This is a IP camera reference design, and basically, if you're into computer vision and you want a nice little Linux system to play with, this is a great little system. So, I don't know. Again, in the classes I normally do, the typical thing that I'll say is, how many of you guys have wanted to design a product that had a webcam in it? You go to Best Buy, you buy a webcam, and you're like, oh, I want to incorporate this in my product. But, you don't have the schematics, you don't have the source code, you don't have any of that. That's what this is. Okay, this is a IP web camera, a fully functioning camera that you buy from us. We give you the schematics, we give you all the source code, we give you everything, the whole Linux PSP, all the source code. Based on GStreamer, The particular part we're using is a small ARM9. It's got Wi-Fi in it. I mean, it's a pretty decked out IP camera. And this is just, I just threw in what it looks like on the inside in case you were interested. Sometimes people ask. And then this is just a really simple little algorithm that I got running in here. And again, this is all done in embedded Linux, and we give you all the source code, and there's actually just a place in the code where we give you the frame buffer. You do whatever you want, and it kicks out. And whatever you do is going to be sent back. So actually, I don't have to show video for this one because I think I still have it. Yeah, I got it running live. So, okay, so what's happening here is he's streaming video. Again, it's an IP camera over Ethernet into the PC. Everything, the PC is not doing anything here other than displaying the video. So all the OCD you see on the top, that's all being done via Linux in the camera. And the tracking is all being done via Linux in the camera. On this one, it's a VGA. Yeah, this is going to be 640 by 480. And it's going to be, I think it's 17, 18 frames per second. It might be 15, but somewhere around there. And then this is just running a simple color blob again. Again, you know, when you get out in the world and you want to demonstrate computer vision stuff and you don't know where you're demonstrating it, stick with simple. I did a class at Embedded System Conference on computer vision, and I tried to do something a little more complicated using edges and stuff like that. And I walk in, and it's a red room for one, with this intricate white edges everywhere. I mean, it was just a noise of edges. It's like, what are the chances? I tested it in the hotel room. Everything worked perfect. So I just stick with simple, you know. So that's the thing. And that's running, again, that's running Linux, ARM9. I think it's 400 megahertz. And you can do quite a bit. As soon as I get the face recognition or face detection software finished up, I'll get it ported on there and get some videos up there. The only limiting factor is going to be the amount of time that you take to run your algorithm. Yeah, it'll do, the camera by itself will do 30 frames per second. Anything you add starts slowing it down. Now, and this particular camera, all the H.264 encoding is done in hardware, so you don't have to worry about that. You actually, it's actually only using for this, like, for a normal camera by itself, it's using 7 to 8% of CPU, so you actually have the rest, so you actually have quite a bit. And then I got another demo. This one I'll show in video. So this is the same concept. This is the RobotVisionToolkit running on WinCE. So in this case, I've got a Roomba robot, and this is a IMX31. It doesn't really matter, but it's basically a PDK based on WinCE, on ARM11 processor. And if you look closely, there's a little, it's hard to see in this picture, but there's a little chip camera up there. That's what it's using as a camera. So let's go ahead and play that. And what did I say? WinCE bot. And this one's doing cone detection. So this, I actually wrote this for RobotVision. There's music on this one. No. So this robot actually travels a lot. It was in Germany last. I got it in my car now, but the idea behind this robot, it just floats around the house trying to find cones. Again, because that was the whole point of RobotVision. It is running on a 532 megahertz ARM, and this particular one's running on WinCE. So it's the same video, it's the same computer vision library, but running on WinCE. I'm just going to show a couple minutes of the video because it's pretty much the same thing. And I slide the cone around, and it goes out and finds it. It's a great thing about robots. You can just tease them all day, and they don't care. So this video is also up on YouTube. It's about 4 or 5 minutes long, but I go into a little bit more detail on what the computer vision is doing and stuff like that. So let's see. Okay. Yeah, I wanted to get into this. Okay, so I wanted to get into Viola Jones a little bit. I don't know, I'm not sure what level you guys are. I mean, I know that I'm working on getting my master's from here, so I know that at undergrad you guys at least cover this. I think there's a computer vision class in undergrad here, right? Isn't there? No? There is a grad level. Okay, well, how many people have heard of Viola Jones? Anyone? No? Oh, man. I got a lot of explaining to do. Okay, so Viola Jones, let's skip right to here then. Okay, so the concept behind the Viola Jones or Viola Jones paper is, first of all, if you may have noticed that within the last, 3 years, 2-3 years, all of a sudden we're seeing a lot of face detection stuff. Webcams can detect faces, little cameras can detect faces, and the reason for all that is because of this paper. This paper is what started it all. Before these guys, face detection was didn't work very well and was extremely slow. These guys in this paper, which is right here if you want to look it up, this paper is what enabled it, at least in the embedded space. I don't know, in the desktop space, different story, but in the embedded space, this paper made it happen because the algorithm that these guys created actually can run real time. And the way the concept works, is it uses these things called HAR classifiers. So a HAR classifier is sort of a different way of doing edge and feature detection. And the thing that Viola Jones created that's unique is they created this concept of the integral image, which I don't know if I have slides for. Yeah, I think I took them out. So they created this concept of an integral image. And an integral image is essentially a pre-processing stage that you do. So what you do is you get the video in, you convert it to black and white if it's color, or if it comes in black and white. And the first thing you do is create this integral image. And an integral image is essentially the sum of previous blocks all the way across and all the way down. So this is 0. You got all your images. You got your grayscale data. In the lower corner, this lower corner is the sum of all the pixels in that image. Okay, so it's a progressive sum. What you can do with the integral image is you can calculate the sums in these squares of the image very quickly. It basically ends up being a total of 8 reads of a table in order to calculate the sum for this feature. So what you do is you take these features and you train them to a bunch of positive images. These are images with faces in it. And then you train them to the positive images, and then you train them to the negative images. You train them that those are negative images. And what you come up with is this array of HAR classifiers that you can now place a scan across any image to find faces. Let me show you what I'm talking about here. So here's your HAR classifier, okay? I'm going to put this over an image. I'm going to take this box. Actually, in that case, it's 2 boxes. And I'm going to put it over the image, and I'm going to calculate a sum. And what you'll see is these are 2 pixels, these 2 boxes here. And as the 2 pixels create a tighter edge, my value goes up. My HAR value goes up. Okay? Or the other way here. So the idea here is that it's going to detect features and edges or differences in a picture. And it's going to give me a value on that. This is actually the formula used for it, which I'm not going to go through. And then, again, if you're doing face detection, I wanted to bring this up. This is the Lfw Database. Have anyone heard of that? If you're going to do face detection, and you need reference images, someone's already done all that work for you. So the Lfw Database includes images of, there's like 30,000 pictures in there, and every one of them's face-centered. So this is great if you're doing face detection. You don't have to go through and do it all yourself. 13,000 images. So I took that database, and I went ahead and trained my features to that database. And the way that works is you create, it's called a detector. You create a detector, and in this case, because I used the database, I could center the detector, and I knew I was centered over the face. And I'm going to apply these HAR features, and I'm going to train these HAR features to that detector. And one of the things you'll get after the training is you'll notice that the eyes are probably the most consistent thing. As a matter of fact, you'll notice that it starts out in the eyes as you do training, and as you add features, it sort of fills out the face. So first thing it detected is the eyes. Now what I'm doing here, the next slide I'm going to show you is 2 HAR features. 1 HAR feature is over the eyes. Now the way this works is it's in the exact same location in every picture of 313 pictures. Okay? And then the other feature is what I call noise or background. It's in the exact same position, but it's not over a face. It's over whatever random background happens to be in the images. And then what I do is I'm going to go ahead and plot that. So I took the sum of those HAR features across 313 images, and this is what I got. The red line is the HAR feature that's over noise or background. And you notice it's fairly well distributed around 0. But see the blue line? The blue line is the feature that's over the eyes. And in 313 different pictures of different people, consistently I get a nice relative consistent value of that feature over the eyes. And what I can do now is I can actually train on that value, I can actually train a threshold where that one feature will actually detect faces in, I forgot the percentage of times, 60%, 70% of the time for just one feature. Yeah, so you can see here. So here's the, again, the feature is fixed in the image. It's always in the same place in the image, but you'll notice that on the left, I get a nice high value for the feature because it's right over her eyes. It's right where it should be because the eyes are darker and the center of the nose is brighter. So you get a maximum value because what's happening is red is subtract and green is add. So you get a higher value there. But over here, the feature, the face isn't lined up. It's not centered right. So over here, I get my lowest value for that feature. So I scan across all those images and I plot it there. And then I calculate a threshold. These are background images. So then I'm going to go ahead and calculate a threshold for that, and I'm going to go ahead and apply that threshold. Now, once I apply that threshold, this analog value that I get out of the feature now becomes a binary value. It's either a 1 or a 0. Either the feature sits above, either the feature, which I'm talking about is this right here, either it's sitting above a portion of the image that it recognizes, which means it's a 1, or it's sitting above a portion of the image that it doesn't recognize, which means it's a 0. Okay? And at this point, once I apply that threshold, it's no longer a feature, at least in the paper. It's now referred to as a weak classifier. Because what it's going to do is by training it with that threshold, I've taught it a feature, I've taught it a portion of the image that I want it to understand. And anytime it sits over that portion of an image, anytime that it sits over a portion of the image that looks the way it's been trained for, it's going to give me a 1. Otherwise, it's going to give me a 0. So it's now referred to as a weak classifier. And then this is a plot, I think this is the same, yeah, this is a plot of HARs over, these are all various locations. It's the same HAR feature. These are all the XY locations within the detector, and this is across all 313 images. And you can see that some HAR features are much better than others. Some of the HAR features sit over a portion of the image that doesn't give me anything, and it's inconsistent. In other words, there's 50% of the time it's one value, the other 50% of the time it's another value, which means it's not very useful. So what I'm looking for is HAR features that sit over a certain portion of the image that's consistent. No matter what face I put under there, it's always a consistent edge. It doesn't have to be the same value, but it should be a consistent relative value. And this is what I get using only one weak classifier, one feature, that one that's over the eyes. If I scan it across the whole image, this is what I get. Now, this isn't all that great. You know, as a face detector, it's detecting a lot of noise and stuff in the background. But now what I can do is I can take a whole bunch of these weak classifiers, okay, which a weak classifier in this case now is a single feature that we've measured that we've measured a threshold for, or we've learned a threshold for. Let me use that term. So a weak classifier is a single feature that we've learned a threshold for. I can take a bunch of these weak classifiers now and combine them into something that's called a strong classifier. Now, there's various ways to do that, and I'm just going to bring up a term here. I'm going to bring up the term. This is with just 4 features, and you can see it gets a lot better. Better, but not great for 4 features. But I'm going to bring up this term called Adaboost, and I'm going to highly recommend you do research. This is going to be in your machine learning class. So Adaboost is a machine learning algorithm, and like I said, you've got all these features now, and you want to combine them to create a strong classifier. The problem is in a 24 by 24 detector, which is what the paper suggests you use, there's 43,000 feature combinations. how do you pick which ones are best? Obviously, you're not going to scan all 43,000. But how do you pick which ones are best? And then how do you combine them in such a way that makes them better overall? And that's what the Adaboost learning program, machine learning algorithm does. So it's going to go ahead and it's going to go ahead and look at these features, and you're going to train these features across faces now. Remember, you're going to train the weak classifier. It's no longer a feature, it's a weak classifier. You're going to train these weak classifiers across all these images, and you're going to come up with a strong classifier. What Adaboost is going to output is a strong classifier. Now, the good news is Adaboost works great. The bad news is Adaboost takes forever. Using a limited set of, 700 or 1,000, only 1,000 classifiers. It took, I actually had to go out and buy a new computer. I went out and bought an i7-920, an Intel i7-920, and then I overclocked it to 3.4 gigahertz. So I got a 3.4 gigahertz, 8-thread, 4-core, 8-thread machine that took a week and a half to do this on only 1,000 classifiers. See, Adaboost is a great machine learning algorithm. Unfortunately, it's an analog algorithm, which means it's floating point. So it takes a lot of time. And I guess that's probably the key thing. Oh, and it's iterative. So it goes through many iterations. And it's interesting. I did some research on the web and other people using Adaboost. And there's one guy who's he did 4 quad cores to do the whole set of 43,000 or whatever. It took 4 quad core machines, 40 days to do it. Who? Oh, that's the multi. Really? That is a good idea. That'd be a fun project, yeah. I didn't know you could. I didn't know you could. An individual could buy into that. I'll have to look into that because that'd be great. Because one of the problems I have with this paper right now that I'm working on is I actually came up with a way to do this significantly faster. Oh, it is easily parallelized, yeah. But the algorithm I have actually, I'm still testing it. But what it did the other day, it did on an Intel Atom, it did it in a day. So, if it works, I just tested. Yeah. It is? Oh, no kidding. I'll have to ask him. Okay. So that would be perfect. And this is very easily parallelized. As a matter of fact, that's why I bought the 8-threaded machine. So anyway, what you end up with out of the Adaboost is you end up with a weight for each classifier, each weak classifier. Those weights then are multiplied, and you end up with a sum which gives you your strong classifier. You then take your strong classifiers and combine them in what's called a cascade. And the cascade now is basically an ANDing operation. So what you're doing is you're going to, you have I think for Viola Jones, their first strong classifier was 200 weak features or weak classifiers. So you're going to pass it through that. If it passes that one, you're going to go to the next one. And the idea behind this is to decrease the amount of CPU cycles required for a recognition. Like I said, there's more information on Viola Jones on my website. Sorry, I had to go through that relatively quickly. But if you're interested, let me know. And that's everything. If you need any more information, emgrobotics.com. I've got a lot of stuff up there. Contact me. All my contact information's up there. Oh, I wrote my own, yeah. No, I wrote my own. Yeah, as a matter of fact, I'm on Rev 3. But, oh, yeah,
if anybody has any questions, I'll bring them the microphone. So just raise your hand.